Today, I'm here to talk to you about the work done with my colleagues from the University of Toronto and YScope. We've investigated managed language runtime implementations to try and understand the scenarios where they excel and where they fall short. I'll explain why JavaScript and Python can be much slower than Java, Go, or C++, and why more garbage collection can actually improve an application's performance. Now, just to be clear, this work isn't our personal attack on your favorite language, but a much-needed, unbiased investigation into understanding the complex managed language runtimes that are only growing in popularity. It is no coincidence that JavaScript, Java, and Python have been the most popular languages on GitHub since 2015. These managed languages utilize runtime environments to provide developers with many useful features. Features such as automatic memory management with garbage collection, automatic memory safety with bounds checking, and dynamic typing, which can greatly improve productivity, minimizing product-to-market time. This allows developers to quickly adapt and improve their applications for the rapidly growing user base. When improved productivity will put an application in the hands of the users as soon as possible, performance rarely starts out as the primary concern of a project. Some even go as far as to claim that choosing a language for your application simply because it's fast is the ultimate form of premature optimization. Now let's fast forward a bit. And now you have a massive user base thanks to the amazing productivity of these languages. Now all of a sudden, users are complaining about things like quality of service, and throwing more money at better hardware just isn't making the problem go away anymore. So now what? Well, you profile your code and you start to optimize it. But this has diminishing returns, as each new optimization requires more engineering effort to achieve any meaningful improvement. For example, Stream was forced to abandon Python for Go, as Python would spend 10 milliseconds creating objects from data that Cassandra only took 1 millisecond to fetch. They stated, "We've been optimizing Cassandra, PostgreSQL, Redis, etc. for years, but eventually you reach the limits of the language you're using." Performance also led Twitter to switch from Ruby to Scala and Java. So performance inevitably matters. Then the question is, how well does each language perform? How do they compare? And importantly, why? This is the question we will answer in this work. So to answer these questions, we performed an in-depth quantitative performance analysis of 4 of the most popular managed languages with the most widely used implementation for each language. OpenJDK for Java, V8 with Node.js for JavaScript, the reference Go compiler, and CPython for Python. We utilized GCC for C++ as a baseline for comparisons. The runtimes we study represent many different designs. We compare dynamic and static typing, execution that is statically compiled, only interpreted, and interpreted with JIT compilation. And we also compare their different concurrency models that I'll explain later. Now, to do this, we needed a benchmark suite. We created a suite of 6 benchmark applications from the ground up that stress a range of components, including CPU, memory, and parallelism. For each application, we implemented it in 5 different languages. We ensure the same high-level algorithms and data structures are used for a fair comparison, yet we keep the implementations idiomatic. But a benchmark suite isn't enough. Existing runtimes do not provide enough observability for us to understand their performance in detail. Therefore, we instrument OpenJDK, V8 with Node.js, and CPython. We provide 2 instrumentations. First, we instrument the interpreter in the runtimes to measure the performance of executing any bytecode. But why does interpreter performance matter? In the past, we were able to brush off interpreter performance by saying everything was long-running, server-like applications. This meant that code we cared about was loaded and JIT compiled, so the execution that mattered was always done efficiently. However, this simply isn't true anymore, as the paradigm shift to cloud applications and parallelism favors having many short-lived smaller tasks. This paradigm requires new runtime instances to be constantly started or restarted on demand, causing startup and warm-up overhead to become the bottleneck. In the most extreme case, we have things like function-as-a-service platforms, where the median AWS Lambda invocation was only 60 milliseconds. Not to mention, some widely used language implementations like CPython are strictly interpreted with no JIT compiler. Therefore, even bytecode level profiling can enable optimizations. For example, Instagram engineers also had to instrument CPython to identify the bytecode instructions with high overheads and then optimize their code to avoid using these expensive instructions. But we also need to instrument the JavaScript V8 JIT compiler. JavaScript is dynamically typed, meaning code can only be checked for correctness when it is executed. For example, this is a function to multiply a variable with itself. This is valid JavaScript. You can call this function and pass it a string. This is also valid JavaScript. A JavaScript implementation must try to multiply the string with itself. And no matter what analysis it can do in advance to know that it will fail, the JavaScript specification says it's only allowed to be an error after trying to multiply the string. The best thing V8 can do is to JIT compile this function and assume x is a number based on profiling your code. Since it optimizes the code assuming x is a number, every time it's called, V8 still needs to ensure you really did pass it a number. V8 calls this shape checking. Our instrumentation allows targeted removal of specific checks in any user-specified function. Removing these checks allows us to see what JavaScript would be like with closer to C-like performance, albeit with some fun C-like undefined behavior that we all love, if any values aren't a consistent type at execution time. So for our methodology, we picked the most popular implementations of our languages and used their latest stable version at the time of the study. We ran the experiments in 2 in-house servers to support workloads with networking communication and measured the average end-to-end completion time. Now next, we'll look at the results of our experiments, and later we'll get into some findings. So this figure shows the results of all our experiments. The y-axis shows the benchmark completion time normalized to GCC. The x-axis is divided by benchmark, with each bar showing a language implementation. From left to right, we have GCC, Go, OpenJDK, V8, and CPython. For the multi-threaded workloads, the number above the bar represents the number of parallel execution units, such as threads or Go routines. At the bottom, we have the absolute completion time of GCC in seconds. Now first, we see the averages highlighted. Go and OpenJDK were close behind GCC at 1.3 and 1.4 times slower on average. V8 and CPython were notably slower at 8 and 30 times slower on average. Now in the extreme case, for the sort benchmark, V8 is 47 times slower than GCC, and CPython is 130 times slower than GCC. Next, let's see the scalability pattern. We can see that V8 and CPython don't always scale well, as shown in the key value store and log analysis benchmarks. In fact, their best performance is achieved when only using one parallel execution unit and gets worse when using more. In comparison, OpenJDK and Go scale similarly to GCC, as they are able to take advantage of multiple cores. However, in some cases, we observed that runtimes can actually provide advantages in performance due to higher level abstractions they provide with efficient implementations. This contradicts the conventional wisdom that abstractions are at the expense of performance. We found a few reasons. I'll explain 2 in the talk, and there's more in the paper. Performing GC can actually improve performance due to improved cache locality, and Go's user-level thread scheduler reduces the number of context switches in combination with Go's standard library using asynchronous networking calls. Now, I'll explain each of the findings. I'll first explain the sources of runtime overhead, namely the type and bounds checking and GC write barriers. Then, I'll explain the scalability limitations of CPython and V8. And finally, I'll discuss the runtime advantages before I conclude. So first, let's look at runtime overhead. We found a major source of V8's overhead to come from type and bounds checking. This takes up to 42% and 87% of the execution time in Sudoku and sort benchmarks, respectively. Now, I'll dive into Sudoku to explain this overhead with an example. So the Sudoku board is just a 2D array of integers. To access an element, we simply write board xy. Now, to do this dereference, the JIT-compiled code must first check that the board is an object. Then it must check the type or shape of the board. Now, V8 checks that x is an integer. Finally, before indexing the first dimension, board x, V8 does a bounds check. After indexing board x, V8 needs to check that it actually yielded a valid element. Since arrays don't actually have to be contiguous in JavaScript, and valid elements are known as holes. V8 then checks if it found an object at board x, and then the type or shape is checked to see if it is indeed a 1D array. Now we are finally safe to use board x, but all these checks are still only for the first dimension. Similar steps of checks repeat for the second dimension, and in the end, we required 11 type and bounds checks to access board xy. Removing these checks resulted in a 1.7 times speedup in Sudoku. In the extreme case, removing these checks resulted in a 7.9 times speedup in sort. Now, another source of runtime slowdown we saw for OpenJDK in the sort benchmark is caused by GC write barriers. With OpenJDK's default GC algorithm, G1, it was 10 times slower than GCC. Just to be clear, in this benchmark, there's no memory pressure, so GC is not triggered. However, G1 must still maintain data structures needed to perform GC in every write operation in order to prepare for future GC, even if the GC doesn't actually run in the future. This is called a write barrier. G1 adds 44 instructions for these write barriers, completely dwarfing the 6 instructions required to swap the elements and the 5 for bound checking the array accesses. Switching to a non-default GC algorithm without write barriers improved OpenJDK's performance by 5 times. Now, recall that in 3 of the 4 of our multi-threaded benchmarks, CPython's best performance was achieved with only 1 thread, whereas other languages can be improved by their performance using more than 1 thread. CPython's fundamental problem is that it has a global interpreter lock. This prevents multiple threads from executing in parallel. Developers can take advantage of multiple cores by creating multiple processes. However, processes have to serialize and deserialize any data they communicate. We tried that, and it resulted in worse performance. Now, V8's concurrency model results in essentially a similar effect. It is event-driven, meaning that it spawns a fixed number of background threads which I/O requests are offloaded to. While those background threads are blocked on I/O, there is a single event loop executing the developer's code in a single thread. Any computation must run in an event loop. So to utilize multiple cores, multiple event loops are needed. But in V8, separate event loops have their own entirely separate heaps, and there is limited support for shared memory. Therefore, computation in separate event loops can only be communicated with each other by serializing and copying data back and forth. The only benchmark where V8 and CPython's concurrency models scale beyond 1 thread is the file server benchmark, where a client requests a file and the server simply sends it back. Here, threads do not need to share memory, and they are purely I/O bound. Now, despite all these findings on the overhead of runtimes, we actually observed a few cases where runtime languages outperformed GCC due to the higher level abstractions they provide. Now, first, we found that performing GC can actually speed up the application. For example, OpenJDK achieved a 1.5 times speedup over GCC in the single-threaded key-value store, which is the largest speedup of any runtime over GCC in all benchmarks among all languages. This was due to GC improving cache locality. In this benchmark, we implemented a key-value store that uses a hash map. Our hash map uses chaining, which means that whenever multiple keys are hashed to the same bucket, known as a collision, the node that contains the key-value pair is appended to the bucket's linked list. This figure shows a hash map after 6 insertions. The buckets are labeled B at the top, and the nodes of the bucket's linked list are labeled N. Now, the dark area shows the layout of the JVM heap. OpenJDK uses bump pointer allocation, so objects are allocated on the heap in the order they are inserted to our key-value store. In this case, the insertion order of these 6 nodes are from N1 to N6. This leaves the nodes fragmented throughout the heap with respect to the linked list, as we can see in the figure. However, during lookup, whenever there is a hash collision, the linked list needs to be traversed. Now, for example, to locate N6, we first have to access bucket 1, node 2, or B1 and 2, then B1 and 3. Because they are scattered throughout the heap without cache locality, each access results in a cache miss. And similarly, this is always the case for C++ when you use the default malloc implementation. But OpenJDK and V8 use a compacting garbage collector, meaning that objects will be moved after GC. Specifically, live objects will be marked following the linked list pointers. And later, after marking, these live objects will be moved from a different memory region in the same order they were marked. This results in the layout shown in this figure. Now, when we look up on N6, even though we still have to traverse the linked list, there are fewer cache misses because nodes are now contiguous in memory, so that multiple nodes will be in the same cache line. This behavior leads to the unintuitive pattern that the more GC performed, the better the performance is. In this figure, it shows that the relationship between the JVM's max heap size and execution time on the key-value store benchmark. As we can see, the more memory we provision to the heap along the x-axis, the performance becomes worse because it ends up resulting in fewer GC cycles. And in fact, we saw similar behavior in 2 other benchmarks. Now, another speedup provided by a runtime is from Go's user-level threads, or Go routines. A Go routine in Go is a user-level thread that multiple Go routines can be mapped to a single kernel thread. Unlike V8 and CPython, which limit computations to a single core, there can be multiple kernel threads on multiple cores running a developer's Go routines. This can reduce the number of kernel threads used and reduce the number of context switches between kernel threads. For example, in the key-value store, client threads send requests in parallel. If there are 256 client threads, for GCC and OpenJDK, there will be 256 kernel threads on the server side, 1 for each socket connection. Many of them will be blocked on network I/O at the same time, resulting in many context switches. In comparison, for Go, there is still 1 Go routine for each client connection, but there are fewer kernel threads that are spawned because asynchronous network I/O enables multiple Go routines to be multiplexed on a single kernel thread, significantly reducing the number of context switches between kernel threads. In fact, for this multi-threaded key-value store benchmark, Go's best performance is achieved when only using 42 server-side kernel threads, even though there were 256 Go routines, resulting in better performance compared to GCC and other languages. Now, to conclude with some related work. Now, there are many existing benchmarks. Some provide novel methodologies, some investigate specific languages, and some investigate specific types of workloads. We are the first to both provide intrusive modifications to runtime environments and to quantitatively analyze when these runtimes improve or hinder performance. We saw performance inevitably becomes an issue as product or service usage grows. Thus, eventually, we must understand and improve the performance of these complex managed languages. We created LangBench to provide complex runtime instrumentations, enabling detailed profiling and detailed comparative analysis throughout the benchmark suite. Lastly, we open sourced all this work on GitHub, and now I'll be happy to take any questions.